Hi guys, we've gone through the theory for shear flow distributions in closed sections. Now I'm going to go through an example. So remember, we're looking at determining this sort of unknown offset Q0, and we're going to then work that out and include that in all of our distributions, and then we're going to solve for what the value of that must be based upon the applied shear load and the moment that it creates, and then the moment due to the internal shear flows. So it's this problem here. Let me move this about. So I have already spent a little bit of time recording a solution to this, but I made a mistake in it, and the numbers didn't seem right as I was going through it, and I thought I would continue anyway and see if I could figure it out as I went along. But I made a mistake quite early in this, so I'm going to show you a quick video of me doing it. So that's the procedure I went through, and so I've got this problem here. Like, this is my previous work. Went through, and you can see it's, I calculated the shear flows all the way down. Doesn't really matter that I'm messing this workbook up. All the way down here, and I realized my mistake was certain here. I was having an inkling that I had some issues up here, and it all comes down to something I did right back at the very beginning. So round here. Okay, I made a mistake in calculating the IXX of this section. Well, not the IXX of this section, but I made a mistake with some basic numeracy, which is unsurprising for me, I guess. So I'm going to start again. I'm going to re-record this whole thing, because even though I could have gone back and I could have corrected it, it would have taught you guys to go through, and you would have been frustrated seeing the error. I'll show you how I knew I made a mistake at the end, okay, and how I knew I'd got through it, because that's important. It shows you that I'm a human being who makes mistakes, but also, importantly, I can recognize when I've made them, and I'll tell you how I know I've made them. So let's put this problem back in here. This is problem 2.2 from the notes, I think. So we've got this problem up here, and we're asked to determine the shear flow distribution. So to determine the shear flow distribution location, that ain't right. It's got to be just the shear flow distribution. Let's cross that one out. And so we've got a constant vertical load of 100 kilonewtons, which is acting vertically here. So we need to determine the shear flow distribution of this shape, and we don't, because it's closed, we don't know the value anywhere. So if it were an open section, we would know that it has to be 0. And we would have been able to use QS is equal to minus Vy on Ixx, and then the integral from s to 0 of thickness multiplied by y as a function of s ds minus Vx on Iyy multiplied by the integral from s to 0, the thickness, x as a function of s ds. So we could have used this if we had an open section. And we said that when we've got a closed section, what we'll do is we'll imagine one end is almost an open section, or we'll replace this expression above for a closed section to QS is equal to Q0 plus QB. So this is then an unknown offset to determine. And then QB is simply the basic or the open shear flow distribution. So it's this one up here. So let's just say this is for an open. This one is for a closed. Okay. Annoyingly, they're both called QS. That's the way that Megson calls them. I'm not going to argue on that. Okay. So we're going to go through this problem. We can see in each of these that we've only got a vertical shear force. We've only got a Vy, so I don't need to use this. So our expression, wherever we choose this one to be open, we're going to use this with QB equal to the expression above with the Vx taken out. So wherever we start, this problem, we'll use QS is equal to Q0 minus Vy on Ixx, integral from s to 0, thickness multiplied by y as a function of s ds. So this equation is going to help us solve this whole problem, and we are ultimately going to determine what the value of Q naught is, and then that's going to give us all of those shear flow distributions. So in this problem, we are only looking for the distributions at this moment. We're not yet looking for the shear center because we don't know how to do it just yet. So let's have a look at the problem. Vy is known. Y is defined as being up, and Vy is 100 kilonewtons down. So Vy minus 100 times 10 to the 3 newtons. Ixx, well, we don't know what this is yet. So this problem, I borrowed this problem from someone else's university notes. This problem is defined where this base down here is defined not going to the centroid of these two vertical members, but it's defined going to the external edge. And the same with the vertical point here. It's defined as being the actual external shape of this object. So we can use these shapes to get to split this shape effectively into an external rectangle and an internal one. And that's going to help us easily determine the second moment of area of this shape. So let's say what these are. So I've got external and internal, and let's just write these down. So the external shape has a base of 200 millimeters, which is 0.2 meters, and it's got a height of 100 millimeters. 0.1 meters. The internal shape, well, we've got the 200 minus 3 minus 1, so it's 196. So base is 196 millimeters, 0.196 meters, and the height is 100 minus 2 minus 2, so it's 96. That's millimeters up there. So I've converted everything into meters here. That's just the way I've chosen to solve this problem. You can make a choice in this problem. You can either choose to keep things in the millimeters. You would then determine your Ixx. It would then be your second moment of area would then be in millimeters to the power of 4. You can make the choice. You could also solve this if you do that and you keep everything in millimeters. You've got to keep your thickness in millimeters and keep all of your displacements in millimeters, and your shear flows will then be in newtons per millimeter. Okay, if we don't do that and we put everything into meters, then we've just got to be consistent, making sure that thicknesses and y displacements are always in the same either millimeters or meters that we're using. Okay, so well, let's just solve these the two ways. So let's say Ixx, remember, is bh cubed on 12. So if we do this using meters, we've got 0.2 multiplied by 0.1 to the power of 3 divided by 12. Okay, that gives me 5 thirds. I'm going to keep that as a fraction because that's exact. And then over here we've got Ixx is 0.196 times 0.096. It's a not very nice number, there's no fraction for that. 1, 2, 3, 4, 5. 1.445 times 10 to the minus 5. So the second moment of area of this object here, which is the external shape, the bit that we care about, is going to be this minus this. That number isn't right. Where have I made a mistake here? Let me have a look. Okay, it's this number here. This number isn't right. It's not 5/3. And I should have been able to see that because that's clearly not right. Again, this shows you it's difficult to sometimes do this live. 5/3 is bigger than 1. This can't be bigger than 1. Okay, so it's 1 divided by 60,000. That's my own stupid mistake there. And I'm going to keep it in. Okay, so yes, that's 0.2 times, yeah, there we go. So that number here should be replaced. Shows you sometimes it's difficult to do this live because it's very difficult to recognize your own mistakes as we're going through. But there we go. So 1 divided by 60,000 minus 1.445 times 10 to the minus 5 gives me a number that is much more reasonable. So I was expecting this to be a small number and obviously got a number that wasn't quite right. So 2.216 times 10 to the minus 6 meters to the 4. That's my IXX for this shape. And again, I did it in square meters. If we'd done it in millimeters, you'll end up with a different answer. You'll end up with, well, we can work it out. So millimeters to, or meters to millimeters is multiplying by 1,000. So I've got to multiply by 1,000 4 times. So I've got to add 12 zeros to this. Adding 12 zeros plus 12 here, you would have ended up with 2.216 times 10 to the 6 millimeters to the power of 4. So you can choose whether you're going to stay with millimeters or meters. But what that enables us to do is that before we even split this problem into sections, we can just replace this with a number. Okay, we can say Vy on Ixx is equal to minus 100 times 10 to the 3 divided by 2.216 times 10 to the minus 6. So what's that? Minus 4.51128 times 10 to the 10. Okay, so my mistake when I first went through this was I didn't have a 10 to the 3 here. So I was actually, 3 orders of magnitude out from this problem, which meant this was 1,000 times too small. Propagated through the whole problem and made a big mistake here, okay? And it meant that my answer was incorrect for the applied loading, and I could have gone through and corrected it, but I didn't want to, okay? So we've got this problem now, we've got Vy on Ixx, and we've got this expression which is going to give us the distribution. We don't quite know yet how to do this, so we have this shape up here which has been drawn using the external shape of the object. Now let's just copy this back in again because I want to redraw this using just the centroids of these shapes, okay? Because we don't particularly care about their thickness, and we've defined shear flows as going from, say, the centroid of this object to the centroid of that object. So we're going to use that definition. So let's draw this. Let's replace this with a we'll ignore the thickness of them, but we'll write them on there. Okay, so that having dissimilar thicknesses here is what enables us to, it means the shear center won't be directly in the centroid, but we know the vertical location of the centroid would be at the horizontal line, defining where the centroid is going to be somewhere along here, is going to be at the vertical line of symmetry of this object. So the distance now along here is going to be 200 minus half of this thickness minus half of that thickness. It's going to be 200 minus a half minus 1.5, so that is 196 millimeters equals 0.196 meters. sorry, that's not one, it's 198. I'm jumping ahead of myself, that was the number from earlier. So it's 200 minus a half minus 1.5, which is minus 2. It's 198 millimeters. I'm just remembering the numbers from previously. Okay, and this vertical distance is the same. It's 100 minus 1, so it's 98 millimeters. So this is now our simplified problem, in that it's not really simplified, it's just that we have written it using these infinitesimal thicknesses on here. So we've drawn to the centroid. We no longer have to think about the shape of the object, or rather we don't have to think about drawing the thickness of the object. So because we've got this applied load here, we spoke about the direction of how these shear flows have to work. So we know that the two vertical members will have shear flows in these directions, two shear flows going down, and then that means that let's draw my object in the background here. Actually, let's just say this is my outline of my section. Those two vertical points are going to have shear flows that go in this direction, and these two are therefore going to have shear flows. In order to be continuous, must be going in this direction. So we've got a continuous distribution in this object due to applied shear force, 100 kilonewtons, and we're going to determine what these actually are. So the significance of where the arrows change direction is that there is a sign change in the definition, in the actual size of those shear flows that we determine. So if we, for example, and what we're going to do is we're going to say this is S1 defined in this direction. This would be, according to our sign convention, the positive direction of S1. But we know, because of the way the shear flow distribution has to be along here, that the actual start of the shear flow as we go along S1 must be in the other direction. So we're going to have something that starts out negative, increases until some point where it switches over to be a positive number and goes there. So all that means is that we're going to have a sign change in both, it would be S1 and S3 for this problem. So let's draw those shear flow directions onto here. This diagram's getting a little bit messy, but that's fine. S1, S2, S3, and S4. So I've chosen in this problem to start up here, okay? So that means that at this node here, we'll call this Q1. Q1 is going to be equal to that unknown offset that we're going to determine. And we're going to determine that at the end of this problem, but we're going to remember this here. So the first shear flow, which is QS1, and in Megson he would call this, I haven't written these nodes on here, let's call this 1, 2, 3, and 4. He'd call this Q12 in this case, but we're going to do QS1. We'll say QS1 is equal to Q0, and we do the minus Vy on Ixx, and we've got a number for that now. It's 4.511. Let's just copy that down. So that's going to be plus 4.51128 times 10 to the 10, and then we've got the integral from S1 to 0, and then the thickness as a function of S, which actually for this is just a constant of 2 millimeters. So I've got 0.002 multiplied by the Y displacement from the centroid, so here up to here, which is going to be 49 millimeters, so 0.049. Probably would be easier to do this problem in millimeters, but I'm going to do it all in meters and just put up with my choice now. Okay, so we've got nothing in the integral that's actually a function of S1, so we can just multiply this by this by this, and then stick an S1 on the end, and that's our answer. So we get Q0 plus, let's do all these numbers together. 4.42105 times 10 to the 6 S1. So this is our first shear flow distribution. So this is the shear flow distribution in S1. Now let's think about what we've got here. So if this is the distribution going from here to here, and this is it's increasing in S1, then Q0, when we find it out, must be a number that's negative and larger in magnitude than this number here, or otherwise we've made a mistake. So that's how we're going to have a look at this and see if we've actually solved this properly. So we've got shear flow along here. And if we were to draw this, we could draw this as at the moment we've got some unknown value of Q0. For the sake of drawing it nicely, I'm going to draw this with Q0 as being positive, even though it's not. And so this shape along here is the shear flow distribution, and the slope of this is that number there, 4.22105. So QS1 is equal to Q0 plus 4.42105. So that's our first distribution here. And if we find out, or when we find out that S1 is a negative number, this will just change this distribution to look something like this if we were to draw it. Okay, that would then give us this positive value here and a negative value here. Okay, we'll think more about how we represent this on the diagram when we get there. But what we want to know is we want to know this value Q2 here, which is the principal value of this shear flow as we get to the end. So let's determine that, and that's just going to be QS2 when S2 is equal to QS1 when S1 has reached its end, which is 198 millimeters. So the end slash principal value Q2 is equal to QS1 when S1 is equal to 198 millimeters. So let's put that in there. Q2 is equal to Q0 plus 4.42105 times 10 to the 6 multiplied by 0.198. So that's Q0 plus 8.75368 times 10 to the 5. Okay, so that's then Q2, that's the principal value. And what this is then the starting value of the next one. So that's then this value up here. It's still a function of Q0. So we have that offset at the very beginning of this Q2 up here. So we're going to find out what QS2 is now. So we're looking down here, we know that it starts at that value Q2, which is actually Q0 plus about 875,000. And we're going to look and work out what the distribution is. So QS2 is equal to, well, let's just copy and paste this number up here. It's equal to this minus Vy on Ixx multiplied by the integral from S2 to 0 of the thickness multiplied by y as a function of S2. So I'm actually just going to call that Vy on Ixx because I can't be bothered looking up that number. Let's say integral from S2 to 0. The thickness of S2, which is 3 millimeters, and then the y as a function of S2, ds2. So let's think of what these are. 3 millimeters equals 0.003 meters. and then y as a function of S2. So let's do it over here. When S2 is 0, y is equal to minus, no, sorry, when S2 is equal, sorry, it's not minus, when S2 is 0, y is 49, and then it's going to be just reduced by S2. So y as a function of S2 is 49 minus S2. So let's rewrite this. Okay, so that minus Vy on Ixx was 4.51128 times 10 to the 10. And let's put these numbers in. Integral from S2 to 0, 0.003, and then I've got nearly made another mistake here. That should be 0.049. Okay, so we've got to be careful there. Because we've got to have this in meters and not millimeters. So let's take the 0.003 out, multiply it by this number ahead of it. Okay, and then we're going to do the integral from S2 to 0. If I could just do the integral straight away. So let's say we've got 0.049 S2 minus S2 squared on 2. Okay, so this is our distribution. Let's I'm just going to leave it like this at the moment. Actually, I'm not going to multiply this out. We'll leave it as it is. Let's work out the principal value. The principal value again is going to be the value of S2 when we get down here. Let's just have a look at this distribution as well. We can see that it's quadratic. And let's have a look at the shape of it. So the principal value is going to be determined when S2 is equal to 98. Let's put those values in. Yeah, okay, that's good. So unlike I did previously, I'm not going to do this bracketed bit incorrectly. So we can see here that when S2 is equal to 0.098, we have 0.049 multiplied by 0.098 minus 0.098 squared on 2. So that is 0.098 on 2 already. So this whole thing is just equal to 0. So our principal value, it just gets rid of all of this stuff here. Okay, get rid of everything beyond the plus sign. So Q3 is equal to Q0 plus 8.75368 times 10 to the 5, which is equal to Q2. Okay, so that means that our distribution is symmetric here. So we've got symmetric and quadratic. Okay, let's just have a look at these. Yeah, it's going to be a quadratic distribution. Okay, so Q3 is equal to Q2, which is also going to be the starting value of the next distribution here. Okay, so the next distribution is S3. That's going to be the next one we're going to calculate. QS3 is equal to the starting value, which is this bad boy, minus Vy on Ixx, and then the integral thing, but I'm just going to copy that number from above up here. And then we've got the integral of the thickness. The thickness here is 2 millimeters. So 0.002, and the y displacement is minus 49 millimeters, so that's minus 0.049 here, ds3. So we can again multiply that by that by that and stick an s3 on the end, and that gives us our distribution. Cute. So let's just copy those two down because I'm lazy. There we go. So let's multiply these numbers together. 4.51128 with 10 zeros, multiplied by 0.002, multiplied by minus 0.049, gives me minus 4.4211025 times 10 to the 6. S3, yes. Okay, so that's QS3. That's a linear distribution. We see that it's going to be decreasing with S3. Let me just think if that makes sense. Have I made a mistake there? Let me double check. Nope, that's fine. That's okay. We're okay. I'm okay. So that's our distribution here. We've got, again, a linear distribution here. And then the principal value that we want to determine is the end value here. So let's say we've got some decreasing value. We want to know what Q4 is going to be equal to. Okay, losing my mind a bit with doubting myself after I made a mistake in this last time, so apologies for that, guys. So we now want to know the principal value here. Let's just copy one of these down as well so we can okay, so we're going to do the last distribution, which is S4 up to either we can call it 0.5 or 0.1. They're the same point there. So the last distribution, QS4, there ain't no Q5 on this, or there ain't no S5. We need that principal value, which I haven't worked out yet. So let's work out that principal value. So Q4 is equal to QS3 when S3 is equal to 198. Or in SI, it's going to be equal to 0.198 meters. So let's see what that is. So it's going to just be Q0 plus that number plus this number multiplied by 0.198. 8.75368 times 10 to the 5 minus 4.421025 times 10 to the 6 multiplied by 0.198. Gives me 5.05. Is that? Yeah, that seems about right. Yeah, that's a small number. Okay. So that is the value of the shear flow distribution, the principal value at Q4. It's going to be the starting value for the last distribution. Let's see if this goes ahead. So QS4 is equal to, there should be a Q0 here as well. Sorry, that's why this doesn't look right to me. 8.57 minus 4. Yes, that's fine. Okay, there should be a Q0 here. Okay, because that's the Q0 up here that I didn't copy down here. So QS4 is going to be equal to Q0 plus 5.05 minus Vy on Ixx multiplied by thickness y, all that integral guff, but we're going to just copy that number down from up here, which is minus Vy on Ixx. So the integral from S4 to 0. So the thickness is, let me bring my diagram up, thickness is 1 millimeter, so 0.001. And then on here, we need to know what's the y displacement as a function of S4 is. So over here, when S4 is 0, y is minus 49, and it only gets bigger. Okay, so we get y is, as a function of S4, equal to minus 49 millimeters plus S4. So that's minus 0.049 plus S4. So we can put that into here now. Okay, and then we can multiply this number over here. Well, that's just knocking off 3 zeros, actually, so that's good. We can just take this to a 7. Let's... Okay, so that's taken that constant out of the integral. Don't like this 5 here. I don't trust that value at the moment. We'll see if it goes. Okay. So I need to just think for a moment. I'll probably pause through this. I'm fairly certain I've made a numerical mistake somewhere in here. Because I don't, where I can see this problem going is that the vertical shear flow distribution in this final member needs to have the same value at the end, needs to just be a function of Q naught. So this number here means that cannot be the case. This number should be 0 effectively. So I'm going to try and figure this out. I think this might be where the mistake crept in here. This number, I copied this down from my calculator wrong. You might have been screaming at the screen when you did it. That number is 1.35338. Not, yeah, let's correct this here. In fact, no, that shouldn't have mattered because it doesn't go into the next distribution anyway. So, because this whole thing is equal to 0, so that doesn't make any sense. This number here, let's just check where I've gone through with these. Have I copied this number down correctly? 4.51128 times 10 to the 10. Right, this number here is incorrect. Okay, this number here is wrong. So that is minus 4.421054 times 10 to the 6 S3. And I suspect that when I multiply this by 0.198, I should get a number that cancels with this. So let's just check that. Yes, I do, okay, which gets rid of that number. So this didn't seem right to me here, and I got rid of that, okay? So just confirm that for yourselves there. I knew that number shouldn't be in there, okay? And I've gone back through and I knew I made a numerical mistake somewhere and made my numerical mistake in just copying down these numbers here. So I'll fast forward through some of that, but I'll lead you through my thought-making procedure there. Thought process. Okay, so this is now the distribution QS4, and this is correct because this number don't belong in there. That's not something that should have been in there. That was introduced because I copied this number down from my calculator wrong, or maybe put it into my calculator incorrectly. But we've got this here now, so this is what I expected. This was not what I expected, okay? So we've got here now, this now gives me the distribution QS4, and what I want to see is that when I get to Q1 again, so up here, going from QS4 up to Q1, I should just have Q0, and my issue was I could see that when I had this number in here, there was no way that was going to be true, because this is just going to be equal to 0 at S4 is equal to 98. then the whole, or equal to 0.09, equal to 98 millimeters, we'll say, the whole bracketed expression tends to 0, okay? So that gives us Q1, which is equal to QS4, with S4 equal to 98 millimeters, is equal to Q0, which is equal to Q1. So that's good. That means that we've determined that we've got this unknown offset, and when we go all the way around the circle, we've propagated all of those shear flows correctly because the end value of S1 is equal to this unknown Q0 at the start. So let's write these all down now. So QS1, QS2, QS3, and QS4. So QS1, QS2, no, that's the principal value. Copying QS2 is what I want. QS3, which I've written none of these nicely, so I'm going to rewrite them all tidily. I just want to be able to copy them all in one go. And then QS4 is this one here. Okay, so let's the problem with this infinite canvas, it's good for doing stuff, but it's sometimes difficult to copy and move stuff around. So I'm just going to make these bigger so I can see them, and then I'm going to copy them into being. So QS1 is Q0 plus 4.42105 times 10 to the 6 S1. Can now erase that version up here. QS2 just copy this down. QS2 is Q0 plus 8.75368 times 10 to the 5 plus this quadratic distribution, which is 1.35338, which is that the correct number now? Yeah, it is the correct number. Multiplied by 10 to the 8, multiplied by 0.049 S2 minus S2 squared on 2. I'm going to erase this one. Q3 is another linear one, which is Q0 plus 8.75368 times 10 to the 5 minus 4.421054 times 10 to the 6 S3. And then this last one is Q0 plus 4.51128 times 10 to the 7. And then I've got this minus 0.049 S4 plus S4 squared on 2. And so the units of all of these are newtons per meter. So we've got these distributions now. They've all still got these Q0 in here. We don't know what this value of Q0 is just yet. So we need to use the fact that for an open section, the moment due to the applied shear force is going to be equal to the moment due to the shear flows anywhere where we load it. Okay, this doesn't matter where we load it. So wherever we load it, we get that distribution. And we can think about this as if we have an object like this, then we've cut it here, or we've sort of pretended we've got this open section here. We've got this we ended up with a linear, quadratic, linear, and quadratic here with this unknown value. So these would be QB1, QB2, QB3, QB4. Remember that QB was the basic, or the value of the distribution without that Q0. So for a closed section, we had QS is equal to Q0 plus QB. The QB would just be the value as if we had this open section. And then we've also got this Q0, which is everywhere. So let's say we've got this constant Q0 that can be added here. So could draw that on with another color. But for our purposes, we know that Q0 should be a negative number to help us, okay? Because that will enable the direction of the shear flows to be correct. And we spoke about that at the start of the problem. So this is going to be what's going to help us solve it. Now we're going to choose to take moments about somewhere in this problem. So let's, for the purposes of this problem, let's redraw this one last time. Let's say so I've got QS1, QS2, QS3, QS4, and I've got this applied shear force of 100 kilonewtons. So we're going to choose moments about somewhere that we can evaluate them, where this is going to provide a moment, and we can evaluate it with the rest of them. We could also choose to take moments about here, and then we'd have to make Q0 such that the net moment added up to these was equal to 0. But we need to pick somewhere where the moment due to this is equal to the moment due to all of these. So I'm going to, in fact, let's choose to do it here. Let's say take moments here. Let's write the word evaluate with the correct letters in it. Evaluate moments here. So what this means is that because we're evaluating moments here, MV is equal to 0 because that applied shear force cannot apply a moment here. So MQ must also be equal to 0. So let's have a look at we can only get a moment from QS3 and QS4 here. So these two cannot provide moments, so we can just neglect them for the moment. I'll put them in brackets. We need to look at the moments provided by these two here. So for loading at this point up here, then MQ is equal to the force due to QS3 multiplied by the vertical separation, or the moment arm, which is 98 millimeters. Let's write this in meters, 0.98. So that's going to provide a, let's say, clockwise moment. Let's just treat clockwise as being the direction for this one, plus F due to QS4 multiplied by the horizontal distance. So that's going to be 0.198. Okay, so we need to evaluate these two expressions, FQS3 and FQS4, just remembering that FQ is equal to the integral QS all the way along. Okay, so we now need these two expressions for 3 and 4. Let's bring these down. No, let's copy the correct thing down. Okay, so I need to, I'm trying to now replace these in here. So I'm going to evaluate these two moments. So we're going to do this first. So we're doing S3, which is horizontal. So we're going from 0.0198 to 0, Q0 plus 8.75368 times 10 to the 5 minus 4.421054 times 10 to the 6 S3 ds3. So this becomes Q0 multiplied by 0.0198 plus 8.75368 times 10 to the 5 multiplied by 0.0198 minus 4.421054 times 10 to the 6 multiplied by 0.0198 squared on 2. I wouldn't do all these steps if I was doing the solution myself. I'm trying to show you everything I'm doing here. So let's work out what this number is. 8.75368 times 10 to the 5 minus multiplied by 0.0198 minus 4.421054 times 10 to the 6 multiplied by 0.0198 squared divided by 2. Okay, so that gives me this value here. Okay, so that's going to be my FQS3. Now let's do the same for FQS4. That's going to be the integral from 0.0. I've buggered this up, haven't I? That shouldn't be 0.0198. That should have been 0.198. So let's cross that out. This is why I did the answer in millimeters previously, because it was easier. Get rid of that. That number there goes. That number there goes. Let's just do that number again, see what that is. Okay. Okay, and now we're going to do the next shear flow distribution and get the force due to QS3. So that's going to 0.098. That was the correct number for this one. That's the total length along QS4. And then I need the actual distribution QS4. So let me copy that down. QS4, so that's Q0 plus, let's multiply this out. Okay, so we need to now integrate this expression. We're going to end up with Q0 multiplied by 0.098 minus this multiplied by this squared on 2. Let's write it out properly. So let's work out what this number is. Everything in here is just a number. So minus 2.2105 times 10 to the 6 multiplied by 0.098 squared divided by 2 plus 2.2556 times 10 to the 7 multiplied by 0.098 to the power of 3 divided by 3. Okay, so we've now got these two expressions that give us FQS3 and FQS4, and what that is, this is then the force that's working along this direction. So I've then got a force FQS3. This is a distribution QS3. It's the distributed newtons per meter along here. This is newtons per meter up here. I've now got these forces FQS4, and so that's acting up here. Okay, so I can now multiply those by the two moment arms that I've got. So we can take these values and substitute them into here. And we know that it's equal to 0. So this first one, 0.198 Q0 plus 86661.363 multiplied by 0.098 plus Q0 multiplied by 0.098 minus 3538.31 multiplied by 0.198 has to be equal to 0 because it's got to provide the same moments when evaluated at this point as the applied shear force, which has to be equal to 0. So let's multiply this out now. Ugh. There are some shortcuts you can take here, and I'm going to see if you can figure them out on your own. So we can get the same bit of Q0. So we're going to have Q0 with these two numbers multiplied together twice. Okay, so we're going to have 2 times Q0 multiplied by 0.0. In fact, let's just multiply that by 2. So let's say we've got, I'm not going to write this down, I'm going to say 0.0388808 Q0, and then let's get the numbers, plus 86661.363 multiplied by 0.098 minus 5338.31 multiplied by 0.198. So Q0 is equal to minus 777,779 divided by this number. Okay, so this is the offset now. I'm going to pause here because I made a mistake somewhere. Okay, I'm back. I was concerned that I got a different answer when I did the than I had done this previously. So I like to redo these from scratch when I do the solutions to show that I can go through and do the procedures I expect you to do. So this here is the offset Q0. Now when I did this problem, defined S1 here. So this is the value of S1. In the accompanying notes, you'll see that I defined it slightly differently. I defined S1 here. And so the number that I got in the accompanying notes for my Q0 was Q0 is equal to minus 674.71 newtons per millimeter. Okay, so I've actually put newtons per millimeters cubed. That's incorrect. Newtons per millimeter. So these two answers are different, and that, you don't have to be a rocket surgeon to tell these two numbers are different. And I was concerned that I got the wrong answer, but I wasn't thinking quite straight. So because this is my offset here, it's a different value. So I had the same value of the slope for these two distributions. So I had, in this example, assumed my distribution started like this with some unknown offset, which would move the whole thing up or down. And then when I did the version in the accompanying notes, I assumed my distribution was going in this direction, and we'd move it all up and down in some way using that same offset. So these two numbers are different because my Q0 from the example we've just done is here, and the example from the accompanying notes was done there. But if I take this and add the rest of the value of the distribution, I should end up with the negative version of this number. So that's going to be my Q2. So Q2 should be equal, let's work it out. So Q2, which is the principal value, is going to be Q0 plus whatever my Q2 was. What was my Q2? It's here, so let's copy that down actually. Okay, so that's my answer here. 8.75368 times 10 to the 5. So let's just do minus 200,000, 789.22 plus 8.75368 times 10 to the 5. Yes, that gives me 674.57 times 10 to the 3. Yes, okay. Newtons per meter. Okay, so we're a factor of 1,000 out because I've done newtons per meter. This is newtons per millimeter. Small numerical error, probably somewhere in here, has led to an issue in the decimal places, and the answer is the opposite way round because the answer is the opposite sign because I've defined my total S as being clockwise for this one, and whereas it would have been in the other direction for this one. So the value of the principal value at each corner would have an opposite sign. Okay, so this is a really complicated example we've gone through. This is again, maybe not really complicated. It's about what I'd expect you guys to be able to do, but because it's time consuming, you should need to check your answers. You need to check you're not making mistakes as you're going through. You can fall down many places when you're doing this, and I always find it's quite difficult to do these things and narrate whilst I'm doing it as well. But hopefully that gives you an indication of how we work out those shear flow distributions in an object like this, or in a closed section. It's exactly the same as we would have done for an open section, but we've got to find out that value of the offset, which is here. And then for an answer like this, if I'd given you this problem, I'd be happy to accept these as your answers, as long as you then wrote with Q0 is equal to minus 200.789 kilonewtons per meter, for example. Okay, I would have been happy with that as an answer for this. So this is the bit that makes it different from looking at those open sections, and just be careful of making those numerical mistakes. Okay, you've seen the implication of them, you've seen how I had to re-record this whole lecture, but hopefully that's given you an example of how we do this one. And there's one further closed section example in the notes, and I'm probably going to record a couple more that will help you guys understand how to do closed sections. So thanks for tuning in, guys. I'm going to record one more, which is for shear center determination, and then I'll do a bunch more examples of open and closed sections for you guys. Thank you.